Oh, which, okay. So are we all good to go?
You are all set.
Okay, so hello, my name is Brian Pachuca. I always find it useful to know a little bit about someone before a talk, so I will briefly talk about my background and dive into some cases where I had the opportunity to fuse together web development, intuitive UI, and informed decision-making. So I graduated from the University of New Mexico with a background in architecture and urban planning, and I'm a full-stack developer on the KPFui team at Computational Fox Architects. I'm also finishing my master's at NYU Center for Urban Science and Progress, focusing on how emergent technologies like machine learning and artificial intelligence can be thoughtfully applied to inform policy and decision-making in cities. So while in architecture school, like many others, I was inspired by Greg Lynn after reading Animate Form, which kickstarted my journey of exploring space and time through digital interfaces. The project above, Cubes, was one of my first scripts I ever wrote in Maya 3D, which had 3 cubes, orange, red, and teal, interact with a field to attempt to change the color of nearby cubes while competing against one another. I spent hours writing the code, but was able to reuse it over and over again throughout the semester to explore new forms quicker than I ever have before. The built environment has the potential to shape the way we think and interact with the world around us. Louis Kahn, famous for his delicate architectural hand, once walked through the bath of Caracalla in Italy. The bathhouse has a 150-foot tall ceiling. Kahn noted that we are capable of taking a bath in an 8-foot ceiling. Yet there is something about a 150-foot tall ceiling that makes a person a different kind of person. This idea is not only about how the scale of space, but it points to a paradigm that we are capable of living in these metaphorical 8-foot spaces, but why not push the limits and live in a 150-foot tall space? And could we design for that condition? Architectural design can be more than the 8-foot ceiling. Design can be as magnificent as the baths of Caracalla. So what does it mean to seek out this 150-foot tall ceiling in the 21st century? It could mean that our designs and forms change based on the factors in the urban fabric around them. Imagine our designs taking into account new forms of data from the urban fabric. The diagram I created above shows the triangular surfaces animating based on the position of the floating sphere, responding to the change of context, animating the form. Upon graduating, I began working for a firm focusing on data science and visualization, where we brought UI, UX designers, policy wonks, data scientists, and software engineers together in the organization to get their hands around big data problems in various areas within the urban resilience field across the world. During this time, I became instantly hooked on fusing together intuitive UI and software development. To inform policymaking, I'll be moving somewhat quickly through an example of a project we got to work on this project. So this is a cover page of what is often referred to as the RRAP report, or a regional risk resilience assessment program generated annually by the Department of Homeland Security to assess the resilience of cities across the United States. These reports can often be over 400 pages long, and you can imagine that there is a wealth of crucial information in these reports for mayors and decision makers when dealing with increasing number of natural disasters. However, we also know that these reports might fall on deaf ears, not because of lack of importance, but because they are cumbersome and too technical oftentimes for decision makers to refer to when dealing with a citywide disaster. The decision-making space for these leaders in this situation is often limited, and for many officials are faced with making decisions on the fly as information is coming in at a rapid pace. So we need to find new ways to make this information easily accessible. One of the components of the RRAP report addresses hurricanes, a major concern for cities along the eastern seaboard. A national laboratory created a database of over 500,000 hurricane simulations. The engineers created theoretical hurricane paths, wind speeds, and landfall locations based on historical data. Our team, in collaboration with the national laboratory, created a probabilistic hurricane information model, which ran simulations for which areas would be affected worst by a given simulated storm. The user of the platform could adjust the bearing, land, and wind speeds of the storm, then visualize the impacts to the coast to understand which areas might be most impacted and where to think about sending first responders. Phi was the first step in turning the paper-based information in the RRAP report into an actionable interactive web visualization to make data-informed decisions. You can see in the slide above, a decision maker could zoom into the digital map and identify substation networks that could be affected by a given storm surge or dangerous winds. Over time, Phi went through a series of updates to include a larger database and more intuitive UI, which enabled decision makers to select coastal cities and visualize the potential impacts to electrical substations and power plants along the coast. The user would select an area, and Phi would query all simulated storms which made landfall in the given area and load in critical lifeline infrastructure assets in the database, such as power plants, water sewage plants, and substations. In this case, the study area is Norfolk, Virginia. The lines you see are simulated storm paths, which would animate across the screen, showing you the visual path of the storms. Here, we are seeing over 16,000 simulated storms processed in real time. On the computational side, the storms were stored in database as strings and processed by our analysis layer, which would calculate the probabilities per pixel and render out a raster image that we would then stitch together on the front end, which was surprisingly one of the harder parts. You can imagine that if there's over 500 storm possibilities in the database and different combinations of those possible, based on where the user selects, we couldn't pre-calculate all of the outcomes. We had to do these calculations on the fly. Our best time was around 4 seconds for around 50,000 hurricanes. We tried 100,000 hurricanes along the entire eastern coast, and we had to restart our servers. Once the storms were loaded in, the raster files were overlaid on the map, showing where high winds in orange were expected and estimated storm surge in blue. Here, the user could click on an infrastructure asset to see the probability of the asset being affected by storm surge or high winds and potential electrical outage. This could help decision makers during disaster planning understand how to prepare for a given storm event. You can see that this infrastructure asset is a petroleum port with a 50% chance of experiencing an electrical outage, given the range of storm possibilities. Here is another example where the area is based on the interpolation of all 16,000 hurricanes to have around 2 feet of flooding. Phi took over 2 years to complete and is an ongoing project and has been in disaster planning or has been used in disaster planning at FEMA. Some limitations are on the simulation side. The wind calculations were created using a wind model, which does not always perform well in certain topographical conditions. And estimating storm surge is incredibly difficult since the scientists need to have accurate values for the local watersheds to depict how much water the soil would absorb and how much would flood. The highlight, however, on this project was that this tool helped the National Laboratory justify additional research and get grants to get more localized topography data to improve the model performance and accuracy. So this was an example of taking that paper-based RRAP report by doing user interviews, concept design, going through a user experience and user interface design process. We were able to create an actionable tool by pairing all those pieces together. And then I'll be shifting gears back into architecture and the work at KPFui. If you're not familiar, KPFui was started by Luke Wilson within the KPF practice as an urban analytics research arm focusing on understanding the urban context of projects around the world. Through our computational efforts, we facilitate fast decision-making, help get city approval, and maximize value throughout the design process. We have a library of built tools to quantify everything from views to energy generation to mobility. And this is just a list of some of the tools that we created over the years. We can also customize these tools to create entirely new ones to cater to the objectives of projects. So we have tools that we've created such as retail visibility, looking at shadow regulations, or also mapping interior routing within office spaces and buildings. Some applications. On the far left here is a project that was focusing on the location, rotation, and terracing of towers, a process that can typically take several months to decide on those final locations. But by optimizing for views and sun exposure, we were able to do that in about 2 weeks. Another project, One Vanderbilt, actually replaced an existing building. And at the time, and even now, there's a lot of discourse around how much shade does new construction in New York City cast to the streetscape. By analyzing the building envelope and the sky exposure plane and adjusting the curvature of the building and the design, we were able to decrease the amount of shading cast onto the streetscape relative to the existing building that I replaced, facilitating the public approval process for the project. So throughout the process of KPFui, doing generative and computational design, we generate hundreds, if not thousands of models throughout our iterative design process. Architects, we end up with too many options, or essentially the Netflix paradox, where designers could spend more time looking at options rather than selecting one, a process maybe some of us are very familiar with. Architects and designers are trying to evaluate each design based on form, performance, and other conditions per project. And the question comes up, how do we facilitate quick decision-making throughout that design process? So looking back at history of how information has been communicated in the past couple of decades, from newspapers on every street corner, to the emergence of digital journalism, to now the abundance of interactive web visualizations, from the New York Times to the Washington Post, especially significant during this past year, when all of us were watching interactive election maps and COVID tracking maps, tracking the virus throughout the United States and the world. We've noticed that it is not enough to read about data. We want to interact with it. So our team has investigated how to effectively communicate with technical and non-technical audiences complex urban topics. So in 2019, the KPFui team released Scout. Scout is a shared web platform that helps our global firm gain quick data-driven insights, present to clients, and engage with the community. Through Scout, designers and collaborators can easily explore and compare thousands of design options, make more informed decisions, and enjoy the creative freedom of visualizing results in real time. One example that I'll go through is in 2019, we collaborated with courts to use Scout to investigate how climate migration might affect how cities today should plan for the future. By imagining a city in the future in 2057, which sees thousands of climate migrants leaving cities which are no longer livable, seeking refuge, the city of Leaside took the right steps to prepare for the effects of climate change by taking measures such as repurposing abandoned industrial land or transforming vacant land into green parks. We use Scout to visualize the possibilities of how the city of Leaside could deploy policies in housing, energy, or public space to prepare for climate migration. We created a digital twin of Leaside in Scout to allow visitors of the website to explore different policy decisions. Imagine as city leaders using a tool like Scout to inform policy by understanding the trade-offs when making a specific policy change. What happens when you turn 50% of vacant land into parks or repurpose industrial lots for housing? So where do we go from here? What we've seen and noticed is that there are specialist teams at KPF, and this might be true for other firms, that have various capabilities and expertise who face technical challenges in deploying their solutions to teams across the firm or creating automation workflows that work across the entire studio. And now more than ever, architects and designers are thrown so many different tools to analyze or gain insights throughout the project. We want to remove the technical barriers which might be preventing designers from accessing these analytic tools or insights by being smart of how we deploy software solutions in the studio. Eliminate the challenges of missing grasshopper components or incorrect versions of plugins, grasshopper crashing, or passing Rhino files back and forth between specialist teams. This can increase the response time of specialists at the firm significantly by creating tools that allow them to have better conversations with design teams and enable designers to start using these tools without having to be an expert in Grasshopper or other softwares. By fusing cloud computations, robust analytic tools, and UI, we can deliver insights to design teams faster than we ever have before. We want to close that technical gap between the specialists and designers and the insights that they want. So we have to improve our designs, understand the urban and social context better in cities, and respond to the changes in the design process more effectively. And in conclusion, software development, when paired with intuitive user interfaces within the AEC industry, can empower designers by removing these technical barriers to insights throughout the design process, enabling teams to better understand their building, site, and urban fabric of cities. Thank you.